But in reality, basically, we have two thetas here, 2D, and that's the cost function. And this is the basically that's how your cost function looks like, that math, right? And you are basically somewhere up, the higher up, basically, the larger cost function. And your goal is to reach to the minimum here, right? And when you're looking at something like this, the idea is just simply like walking. You're walking down here, right? So it's not bouncing back, but that's just conceptual for you to understand that the gradient gives you left, right, right? Also, if you're looking at this, a function like this has different minimums, you see? So it's like, idea is, think about this again, if you're going down the mountain and there are different endpoints, you could basically end up at any of those, but you don't know actually if this one is better than this because you haven't reached to that. So if I'm reaching here and that's the minimum point at that location, that's my minimum because I don't have a knowledge of this value, okay? So just keep that in mind. So, previous lecture, we went over the linear regression, and we learned that we can solve in two ways: either closed form solution, that means we take a derivation, set it to zero, and solve for it. We also learned that you can solve using closed form solution if the matrix is invertible, which that means there are a couple of conditions you need to check for. One is that to be full rank, or if the number of columns are more than the number of rows, then you couldn't calculate that. Also, if the matrix is large, the number of columns is large, it's going to be expensive, so don't do closed form solution. We do gradient descent, and gradient descent, the idea is that you iteratively basically solve the problem by guessing, by starting guessing the initial theta, test it, see how good it is, calculate the gradient, update, continue, and then you reach to some convergence and you stop, right? Now, so far we just talked about linear regression. Now, before we move forward, we want to talk about the limitations of linear regression. Okay. So first limitation, let's say I have this data. Okay, this is, for example, x1 and this is y, the target. You have a simple linear basically data, and your goal is to fit a linear regression line to this. Where do you think the line goes through? Like if you solve this, where would you draw this line? Louder, because I cannot hear if you say something. Throw an idea. Where would you draw? I'll give you a pen. Where would you draw this line? This one? Yeah. So, any other answer? Think outside of the concept of the linear regression. Where would you, if you want to draw a line, what's the properties of the line?
Connecting all the points.
Right. Okay. But where does the line starts from? A simple line. Doesn't matter how many times you solve linear regression, this is the line that you get, not this. all of these lines, anything that starts or goes through the origin is the solution that linear regression is going to give you, which is bad, right? Because that's the line that you want. So that's the first limitation of linear regression, is that it's a linear line and line starts from the origin, right? How could you tweak the linear regression problem so this line doesn't start from the origin anymore?
Constant.
Adding a constant or intercept. Line, we always, for line we knew was, for example, ax plus b. That plus b, that intercept, the reason was that you allow the line to start from anywhere than the origin. So that means if you want to, basically it starts from here, you need to find what is this value. And we call this basically, we're going to call it theta 0 for this time. Another way of thinking is that if you centralize your data, that means that if you shift all your data by this much, you know, imagine all your data are 2, 4, 6, 7, and I find this number is 8, and I put all data point minus 8, then that point becomes the origin. Right? That's another way if you want to basically change the scale. But in reality, you need to find that, because otherwise linear regression always fits the line through the origin. So what does that mean for solving the problem? That means anytime you solve linear regression, if this is your data set, which has n by d, that's your input data, what you need to do is to convert this to, let's call x prime, which has n by d plus 1. You add one new column to it at the beginning and all 1. So when you want to solve linear regression, you need to take into account there is an intercept that I need to find, okay? And for that intercept, what we do, we basically add one column at the beginning of the data frame, all constant, 1, 10, 5, 0.5, just should be the same number. I'm going to tell you later why we pick 1, why it's easier to pick 1. But now, so previously we would have, for this problem, the theta that we would learn was d times 1, correct? Now the theta that we are going to learn is going to be d plus 1 times 1. Right? Because we added one new column. So that one new column also has a parameter that you need to learn. And we are going to call that theta 0, which is the same as b. It's just, you know, for convention, we're going to call it theta 0. So from the learning perspective, everything that you learned so far, it stays the same. Nothing is going to change, because this is prior to solving. This was your data. Before you try to find the linear regression model, I massage the data, I add a column of 1 at the beginning, then I solve for it. So from your model perspective, nothing has changed, right? So that theta 0, so the reason we pick all of this to be constant is because for every data point, the starting point should be here. You don't want it to vary across the different data points, right? So that should be the same number. But why 1, for example? Because if I learn theta, theta is a direct scale. So that means that if my prediction was, or let's call it f of theta, was theta x1 plus theta 1 x1 plus theta 2 x2, now I will add a theta 0 plus theta 0 times 1, because those are all 1, right? Now, if it was 0.5, this becomes times 0.5. If it was 10, it becomes times 10, right? The difference here is that the smaller the value or the larger the value, you need to scale the theta with the same ratio, right? So the theta 0 that you learn either going to be larger or smaller. So if you select 1, that's going to be just straightforward. Just, you know. Again, it doesn't matter what the number you pick, the theta will be scaled with that ratio. Is that clear? Anyone? Yes. This part? So do you agree that we have theta 1x1 theta plus theta 2x2 plus theta 0? Why theta 0? Because so we added a one new column, so we have one parameter, right? And this parameter, this column, they are all 1. So this by default is supposed to be times x0. And because x0 is all 1, we just can drop this, correct? Now, if I rather than 1, I pick 10, right? So whatever is this value becomes times 10. That's the solution that you get for any data point when you want to make a prediction, right? What does that mean? That means this theta 0 that I will, if the column was all 1, I will learn theta 0. If the column is all 10, the theta 0 that I will learn is going to be exactly this one divided by 10, because it should be with the same ratio, smaller, right? If it's 0.5, 0.5, it's going to be theta 0 times 2, right? Depending on what's the value of the column you pick, the theta is going to be scaled with the same ratio. Does that answer your question? All right, so that's the first limitation of linear regression to keep in mind, that anytime you want to solve linear regression, step 1, you need to add this column of 1 or a fixed number at the to your data set. Now, go to second limitation. So second limitation of linear regression is that basically the thetas or the features that you have in general are or thetas, what is this called, thetas? So the thetas are linear with respect to your model, right? Which means that if, for example, I have I'm predicting the price of the house. This is a good example. Let's say a square feet, number of bedrooms, and so on. I have this, right? And I develop a model. The model calls theta 1 times the square feet plus theta 2 times number of bedrooms plus so on. This is the model, okay? Now, let's say you are given a couple of examples. Example 1, you have the following house. You have 800 square feet, 1 bedroom, and whatever. Example 2, I have 800 square feet, 2 bedroom, and whatever. Okay. Then we have example 3 and 4. Example 3 is we have 1,000 square feet, 7 bedroom, and whatever. And example 4 is 1,000 square feet, 8 bedrooms, and whatever. We don't get, when I say whatever, that means that, so between these two, between the first two, this whatever is constant. It doesn't matter what it is. And between these two, this whatever is the same. That means they exactly have the same features. Okay. So let's make a prediction using the formula that we have here for each of these houses. So the price of house 1 basically becomes theta 1 times 800 plus theta 2 times 2 plus, right? And house 2 becomes theta 1 times 800 plus times 1, sorry, theta 2 times 1, because this is 1 bedroom. 2 times theta 2 plus 1, correct? And so on, we're going to write it for theta 7 and theta 8. Sorry, example 3 and example 4, 7 bedroom and 8 bedroom. 1,000 theta 1 plus 7 theta 2 plus 1,000 theta 1 plus 8 theta 2 plus. And those are the, we don't need to know what's the price. Those are the price of that, right? Now, let's say you are the data scientist and you are working in a company or your own company, and you develop a model that is going to predict something like that. How price of the house or anything, any is a linear problem. And you have your model, and you know your model when you use it for prediction, it's like you use your evaluation, and you're like, oh, this model works fine. Right? Like the error is low, the accuracy is high, and you are happy with it. But there is one part that after any modeling you need to do, and that's called error analysis. You need to understand that if this model actually logically makes sense, right? So if I'm looking at this two model, what I can do is that for this two house, like I'm interested to see what is the price difference between 1 bedroom and 2 bedroom. Okay, delta y. So basically, if I do price of the 2 bedroom minus price of the 1 bedroom, because everything is the same except for this column. So what do I get? I get theta 2, right? So this is theta. That's whatever is the value of theta is the gap of the price between the theta one, house one and house two. Does that make sense? Yep. So if I do the same thing for 7-bedroom and 8-bedroom, and here also the only difference here is this part, right? So I get basically theta 2. Right? Now, you develop this model and you're looking at the result of this model. What would you say about this model?
Like houses with 2 and 1 bedrooms are similar priced as 7 and 8, something like that. But that won't be correct, obviously.
Why not?
Because like the theta 2 that we have received is like, since like obviously the house which have 7 and 8 bedrooms, ultimately the square feet area is also larger, right? So that it hasn't taken into account because it's getting nullified sort of with theta 1, and theta 2 is we are only getting one value, 8 minus 7, 1.
The square feet part, that's correct. What else you could see about them with respect to theta 2? You're on the correct path.
The difference is same for both the.
So I have a model that it's supposed to predict the price of the house, right? Which statistically it does the job. But if you think about it, anytime you want to buy a property, the largest increase in the price house is from 1 bedroom to 2 bedroom. From 7 to 8 bedroom, you shouldn't see that much increase, right? So this two, it shouldn't be the same thing. You should see higher increase from 1 bedroom to 2 bedroom rather than 7 bedroom to 8 bedroom. So what does that tell you about the model? That my model doesn't understand the non-linearity in this data. Because this is a linear model. Everything linearly increases with one linear parameter, right? So if there is some non-linearity in this concept, your model doesn't understand it. It's a linear model. So that it's a limitation here, right? And again, anytime you use linear regression, keep that in mind. After the model is done, look at some of the result, break it down. See, does it make sense? For example, does it make sense if I tweak this value by 5, all of a sudden the result went by 1 million up? Does it make sense? You need to understand this is because from the model perspective, everything is linear, right? Now, how would you solve this? Your friend here had some ideas, like for example, how could I basically fix this so it actually has a better representation of the price of the house? You could create new features. I could, for example, rather than a square feet and bedroom, maybe I could create a new feature, a square feet times bedroom, right? And learn that feature instead of the two separate, right? Because in that scenario, one here basically is going to be 800 times 1, 800 times 2, 700, 7 times 1,800. You see the gap now is 1,000 here, and here is basically 800. Right? And then for other features, basically you come up with new features, basically. Some sort of features that they are going to account for non-linearity in the data. Sometimes you have those knowledge from either you have someone in the company, domain expert, someone tells you that, oh, I already worked on this domain, use these features. Or you do research because as part of being data scientist, you need to do research. You need to look online to see if someone else has solved the problem. Is there any paper published? What's more, or basically just simple search on like what is important for the basically determination of a price of the house, right? And sometimes you don't have those features. You need to create those features, right? So keep that in mind. Just if you simply use the features that you have, you might have a problem, something like this. Right? Does that make sense? Okay, so first one, I'll give you one in-class problem before I forget. Prove that any norm is convex. We already proved that for Euclidean norm, right? Norm 2 that is convex. You want to prove that any norm is convex. Don't try to take derivation of all possible norms. Use the different definitions of norms to prove it's convex. Okay. Use the convex definitions, for proving. Now let's go to here. So we say that you need to create new features, but let's say you don't have a domain knowledge and you just want to create new features. How could you do that? So we're going to learn something called basis expansion. Okay. So basis expansion are basically, there are some set of nonlinear functions. There are some nonlinear functions. It could be also linear, but normally is nonlinear functions that you apply to your data to create new columns, basically. Like you have D columns, I have some nonlinear function, I apply it, now I get D prime columns, and D prime is supposed to be larger than T. It's kind of like as part of feature engineering that you do, you basically create new features. So that's basis expansion. So basically some nonlinear, could be also linear, let's emphasize on that. Linear functions to create new set of features. Now let's look at one example. Let's say I have y x1. I have the following data, okay, and I only have one column x1, and basically that means I have this 1 and x1. By default, I'm always going to, moving forward, add the column of 1, the number 1. That's the intercept. So this is your original data now, and you fit a linear regression, and linear regression is a linear line that goes through the center of this point technically. So it's going to be something like that, right? A bit up and down, doesn't matter. So that is going to be the f of theta x. That's a model, that hypothesis that you're going to learn, right? But if you're looking at this, I would say that, okay, that's not the perfect line that I want. I need a line to actually go through these curves, right? Something like this, right? So how could I learn a line like that? And then that's where you basically apply some basis expansion, some functions that will create new features. And for this example, what I will do here is that I create a new feature, x1 to the power of 2. Right? So I added one new feature, which is x1 to the power of 2. And if you learn this model, it's going to be this, basically. Of theta prime x. That, if you just add an x2, you're going to learn that curve. Right? Not necessary. It's just, okay, this dots that I'm creating is a simple data. Overfit means that if I have data line like that, I could put something like that. Linear regression is a line that goes through the center average of the points. So this exactly goes through the average. So that's not overfitting. Right? Overfitting means that when you follow a pattern, that means I have a model that does this. Exactly, connects every other point to each other. So that's overfitting. So now all I did was I created new features using some basis expansion, which just basically I went to a polynomial degree 2, and now I have this one. I'm going to use this. I said polynomial degree, so if give you another example, if I have x is x1, x2, x3. We will have this type of functions later, but if I go polynomial degree 2 over this, how many features do you think you get? Polynomial function that you haven't had? To the power of 2, 9. If I have 3, I will get 9, right? Polynomial degree 3 to the power of 3, right? So now, but how does the polynomial degree 2 work? Is that basically you get x1, 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 x2, x1, x3. So the way that's, because it's a polynomial degree 2, any new features that you are creating should be as a power of 2. 1 times 1, that's power of 2, you see? This times that, power of 2. So if it was power of 3, you need to have another value also here. Now, that's the concept of polynomial. So if it's for any power, you need to have that many variables in each set, right? So then it becomes x2, x1, x2, 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 x3, x3, x1, x3, x2, x3, x3. So now the first thing that should come to your mind is that, okay, some of these features are the same almost, right? Which is, but yes, that happens. And also you will have correlation, right? So when you create new features, one of the problems of creating features using these functions is that you will end up with some sort of multicollinearity because there's correlation. You're multiplying features by each other, right? So that exists, but it's also if you don't do something like that, you basically end up with a line a model that doesn't understand the nonlinearity. So you need to basically do both scenarios, find the balance between which we're going to talk about. So this is an example of polynomial degree 2 expansion. Right? It could go up to degree m. So imagine how many features you will create. Now think about it. If I have here, I have only 3 columns. What if you have 1,000 columns? If you go to polynomial degree 2 also, it's going to be so many new features. And that's a problem with machine learning when we say curse of dimensionality, is because you solve a problem and it's not solvable by a set of features you have. So you need to create new features. All of a sudden you end up with so many features that you don't have enough data point maybe for it. Curse of dimensionality happens, right? So then you need to do dimensionality reduction, or you need to get rid of some features to be sure that it echoes. But in reality, the original data that you have might not have that many columns, maybe thousands. If it's in genome, you might have millions, or even if image processing, you have millions actually. But if you say let's say you're doing e-commerce and you might have 1,000 columns, but then you do some feature engineering, you end up with like 10,000 columns. See, so because you create new features in order to be able to have a good model, right? So
like polynomial degree is just only a way to do this basis expansion, or
that's example. This polynomial degree is an example of a basis expansion, right? This expansion could be any nonlinear or linear function that you add to your data. When I say linear, because you might have a function that gives you exactly the same thing, right? But what is any nonlinear function that you apply to your columns and you basically create new set of columns, right? Polynomial expansion is one of the common one. Yeah.
We create this for extra features to make our data linear.
To what?
To make our data linear.
To make your data linear. No. So your data is let's wait there. So what your friend is asking that this data is non-linear, right? Are we creating this new feature so in a higher dimension that becomes a linear data, right? Could be yes, could be no, because there's no guarantee if I go to higher dimension is a linear. Linearity it's not guaranteed, but yes, that could be true that you go to higher dimension, now your data is a linear data in that dimension, right?
So basically what's the use of that, like to add the extra features?
So if you didn't add that extra features, this is the line that you're learning, right?
So it will.
Now I basically learned that one. This is just an example. So if I want to plot that as a function of 3 features, so if this is y for the same thing, this is x1, this is x1 to the power of 2, right? Now, for the sake of this example, this data, if you plot it in a 3D, you will see it's going to be, for example, a linear line now. Now, I will fit a linear line basically through that, right? This is for the 2D, basically, that's the original data. You take it. But there's no guarantee if I go into a higher dimension that becomes a linear data. Just keep that in mind. It could go linear, but there's no guarantee. Right? Now, so we have basically, so also for basis expansion, in your book, you will see this term phi. Okay, phi of x. And I think if you go to Bishop book, you don't see x itself. It's always phi of x. So that means a new version of the data is an expanded version. Because in the book, the assumption is that you have done your data engineering and you created new set of features and you are using that. That's the meaning of that. Okay. So phi of x, if you see, it means basically you have done all the data engineering and you are using, instead of x, you are using expanded version of x. Right. So if you use that, you're basically going to learn this, for example. Your line is going to be theta 1 x1 plus theta 2 x2 to x1 2 plus theta 0, and so on. It could be so many features, like all to the different powers. Now, why would you do that? Do you still call this a linear regression or no? Why? With respect to? That's correct. The expansion is over x. It's still linear multiplications of thetas. So that tells you that doesn't matter how high dimension you go, basis expansion you do, at the end, whatever you learn is a linear multiplication of theta by whatever new features you have. So it's still linear regression. Because remember, we call this linear regression because of this. The dot product between theta and x, right? Now, before you solve the model, you as data scientist, you did some feature engineering. Now you created a new data set with new columns, right? So you're going to use that. That means if I had originally a column which was like this, for example, I have D columns like n by D. But let's say one column is 1, 2, 3, so on. And now I created a new feature, which is 1, 4, 9, to get to the power of 2, and whatever. And now I have n by D prime, right? That's my new data set before the modeling, right? Now, when I want to do the modeling, all I need, I'm just going to use this. So from model's perspective, model doesn't understand whatever feature expansion you have done. This is the data that you're using, and it's going to give you a linear model, right? So that's why it's linear always with respect to thetas, because first you done this, then you do modeling. Does that make sense? All right, so yes.
Suppose we have our data set and we have less number of features, and we are just doing some machine learning stuff to learn our model, and it is performing a underfitting on that. So if we add this kind of basis expansions, so it will going to help in that case.
It could even hurt. Right? So there is no guarantee when you go to higher dimension, again, it will help. It might overfit your data, right? So so we talked about this in MLOps course, that majority of the time that any of you in any company in the future you will see spend on modeling goes into data engineering. You're going to have, if you do a project, maybe 5%, 10% of your time is going to be modeling. 50% at least is going to be data engineering. Because the whole idea is that you have data, and if I have a clean data, there are a limited number of models out there. You can try all of them in a really short amount of time and figure out which one you want to use. But even if you find the best model, if the result is bad, what would you do? Doesn't matter how many times you tweak the parameters or alpha, or lambda, or whatever, the model is not going to learn much. That's why the view is called, so we have model-centric AI or machine learning, data-centric. Model-centric is whatever you do in the school. You download the data set. The data set is fixed. You try different models and try to beat the benchmark. That's a model-centric, right? We have a data-centric AI. That means that when you have this data keep coming, your model is going to stay fixed. You're not going to try to change it so much. You keep hammering the data, creating new features, try to improve the data. You know, even if that means that to go over the labels to be sure the labels are consistent. That's basically what you will end up doing. That means that when I try to have a model and I have a data set and I try it and the performance is bad, by default, you need to go to create new features. Maybe it improves. Sometimes maybe it hurts, right? Because Going to higher dimension not necessarily means that you will have a better result. Maybe you need to actually go to a lower dimension, right? So you need to basically explore different paths, up, down, to understand which one will work, right? Or sometimes, but also think about it. Basis expansion is some statistical way of using the data that you have by multiplying them together, using the same data just to create features. And because this type of features there are lots of collinearity, it's multicollinearity, correlation, high correlation, right? That might actually be bad. So there are lots of time when you want to create features, you're actually going to do manual like handcraft. That means that I'm working, for example, healthcare, and I'm trying to predict a disease. I will go have some interviews with some clinicians and say that, hey, if you are reading these images, what is exactly you look for in order to call someone has a disease? I collect that information, then I come to my data. Okay, I don't have that. How could I predict that? I look at, for example, maybe there is a function out there that says, if you multiply this by that, gives you that number. You see? That's how you create features, but using domain expert. The basis expansion is just an idea that you need to create new features in order to learn some nonlinearity. Either that is going to be using a statistical function or it's going to be used handcraft features. Answer? Yes.
Excuse me. Do we start from data engineering and then move to the model tweaking, or we start from model tweaking and then
it's a loop. So this this is the life cycle that any of you in the future is going to work on. There's going to be data, model, basically deployment. And this is normally has 5 arrows than 3, but I make it simple. You have data, you clean your data, everything is ready, you go do modeling. Then you analyze your model, model is good, you deploy it to a customer. Customer data comes back, oh, the model is bad. Now you have new data because you collected new customer data. You go look through it, update the model, go back, model is still bad. Because what is going to happen, any company that you go to work, companies is not like that they develop a model for fun. They develop a model, and sometimes that model is going to be in that company for the lifelong of that company. Right? Just like, for example, Google has search. That search engine is going to be there forever. Right? So what they do every month, every year, they're constantly updating that model to be sure that model works better, right? And how do you do that? When you deploy, you monitor, and you will see that your model performance goes down by default, because we will talk about it today. There are some data out there that you never saw, like the data that they had for developing a model. Imagine right now, for your project, you go download the data. Data is fixed. You don't have any other option. There's a data you need to download, and you have a model. Imagine you put that model in online, and people go start using it. As soon as people are using it, you see that it's something called basically train serve skew. That means as soon as first user use your model, they're like, this model doesn't work. Because why? Because the model only saw that small portion data that you have. As soon as you see real data, it shows the nature of it. And that loop always exists. And majority of this time goes around here. Believe it or not, I personally do I don't like it, lots of data engineering. It's not fun.
This is model drift, right?
What's that?
This is model drift, right?
So degradation model drift is one of them. Model drift means that if your model, so by reality, that's not, I'm going to pass from this script, but the reality, if this is your model and this is the accuracy, as time goes, this goes down. Any model that you develop in the field, as time goes, the performance of model goes down. Your goal is that at any point like this, collect data, calibrate the model. Now your model starts from here. Again, goes down. Then at here. So you see, any model will degrade. That means the performance goes down. Your job is to make it slower. By collecting data, iterate. At some point, when you get here, then you need to go back. Now I have enough data. You go back and say that, okay, maybe we need to develop, maybe by that time, you need new technologies out there. Maybe we need to use a different type of models, right? But that always happens. You always define a threshold. If I reach this, calibrate. All right, let's get out of that. This class is math, not theory, not concept. So, so that would be the basis expansion. Now, so far for the linear regression, what we use the following cost function. Right? We say that let's use norm 2 basically, right? Or basically Euclidean norm. And I say that, you know, that's a decision. There are other type of cost function that we can use. But what I want you to remember today is the decision that you make for cost function can have a huge impact on the model that you get, right? So let's just start with this. If it's j of theta, cost function means over all of your data. Loss function means over 1, right? And loss function over a data point I basically is whatever you predicted minus whatever actual thing to the power of error square is a square error, right? So what you want to do is that try to understand this loss function, or that is cost function, to see that how does it work? What's the nature of it? If I use it, does it make sense? Is the problem that I'm solving? So this is error, right? This value is the error. And this is error to the power of 2, right? So this is error to the power of 2. Now, error itself, yi hat minus yi, is either positive or negative, right? It's from either direction, correct? So if you plot this, the shape of this error line, how do you think it looks like? Look at you, right? Paramount, right? So this is supposed to be 0. Okay, let's assume that's a 0. That's the error line. You agree? Because everything is to the power of 2, basically. Now, this point and this point is going to be -1, +1, and this is 1, right? Anything between these two, the error square is basically is less than 1. Now, let's say I have this data and I fit a line to it perfectly. This is my line, right? And you know the error is small. Now you see 3 data points here. What do you think will happen to the line? Shift down, right? Or do you think it will basically falls down? Because it also will change the intercept, right? But why? Why do you think this line will drop? What could you see in the error function that we used? If you are looking at this L2 norm, anytime that your error is between minus and 1, the error square is also less than 1. As soon as you exit the -1 and 1 boundary, your error increases, right? So what does that mean? That means this specific cost function is going to be super sensitive to outliers. Because outliers, if this is your line, you have 3 points here now, the errors for these 3 points are going to be super large. Because whatever is the distance, if this is the error, now you need to take it to the power of 2. So those 3 points are going to have a huge impact on the error. And because the goal of this cost functions, or if you do gradient descent or closed form solution, is to give you a theta that minimizes the error. Which theta that gives you the lowest error is the theta for a line that is close to these points. So in the next iteration, your line will go as low as possible to get to those points, because that's where the largest error exists, right? In the next iteration, now you have all the points above to be far. You see this, you keep bouncing back and forth between the line between these points, and you cannot land on any proper line. You can find something between, basically, you know. But why is that? Because the norm 2 is sensitive to large errors. That means that if you want to solve any problem, look at the error range, possible error range that you have. If you think that your error range is within -1 and 1, norm 2 is a good basically, or Euclidean norm is a good basically cost function that you can use. If your error goes outside of that, that could have impact on the learning that you have, because your model could bounce back and forth and finally find somewhere in between, right? Now, so you might say that, okay, how should I know that? Think about what you are predicting. For example, if I predict price of the house, and if I directly predict the price, it could be in hundreds of thousands. That's a large number. So the square of that is going to be much larger, right? So I shouldn't use norm 2. How could I, for example, apply norm 2 to that problem? Maybe I could scale down the column, the price, right? So rather than I predict the price in thousands, I predict them between 0 and 1, and later multiply it by whatever is the scale value. Right? In that scenario, I can use norm 2 as a cost function. Right? So that's the first thing to remember about norm 2. Does that make sense? Anyone wants me to go over it again? Okay. Yes. Again. All right. So we have this basically loss function that it takes any error to the power of 2. Right? If I want to plot this, basically, how do you plot a function? I think we talked about this, but all I need to do is that find a range of values. Let's say I pick from here to here randomly errors, and I calculate the square of that, connect those dots together, and draw a line, right? And that's the form of this loss function. Based on the form, I know that because this is error square, anything within range -1 and 1, maximum will cap to 1, right? But anything outside of that, if it's 2 becomes 4, like this is double basically, right? Or to the power of 2. So that means if I'm solving for a problem where outliers could exist, where the error is large, error is like in tens, in hundreds, in thousands, I should not use this loss function because the model will fluctuate a lot. It will have a hard time to converge. Right? So that's the thing. It's like if you have a large error, don't use that. Now the question is that, okay, what else we could use? So we are going to talk about the type of regression called robust regression. They call it robust because it's supposed to not be sensitive to the outliers. Okay? So robust regression says that if rather than this Euclidean norm, you use basically norm 1 as the cost function. What was the definition of norm 1? The summation of absolute values of elements, right? So that means this is summation of theta transpose xi minus yi, absolute value, or absolute error, basically. So the loss function is Li is basically absolute value of the error. So now let's see how does that look. If this is error, this is the absolute value of error. Everything is linear, right? So it's going to be like a V. Right? That's going to this is how this cost function or loss function looks like. Because error, exact same value as positive. So now this here +1 and -1 doesn't matter. If you go outside of it, the error stays in the same almost. Right? So that means that if I have the same line, if I have the same line here, I have these outliers. The line that I will get is still almost the same because it's not going to be sensitive to the outliers that much. It will change the line by a bit, but just small because the line is more focused over those data points, the majority of the data points. Now, if you're looking at this cost function, what do you think is the problem, mathematical problem that you can find here? Not conceptual, like mathematical problem. If you want to, for L2, what did we do? We put it in a logistic regression, we solve it using closed form solution or gradient. If you use that, what do you think will happen? Could you do a closed form solution? Can you take a derivation of absolute value? Yes, no, no. You cannot. So what will happen here is that it has derivation for here and here. It doesn't have derivation out here. So that means that the derivation of j of theta with respect to theta at its is undefined at e equals 0. The other one is just linear. So at its minimum, the derivation is not defined, right? So, but that doesn't mean that we cannot use it, because we are using it and we call it robust regression. But that means that you cannot do a direct derivation. So there are some techniques that you can use. It's called, for example, subgradients. We don't need to learn that for this class, but subgradient is like a bit, rather than taking a full gradient, you basically break it down into a part and try to solve it like that. So for L1 norm, we use a technique called subgradient to solve it. Okay. Now, so okay, the idea was here is that, okay, how could we come up with another cost function that doesn't have this problem of the derivation at its minimum? And that's where the third one basically we call Huber loss. That's a new cost function that we have. So interestingly, it's so Huber loss basically, it's a combination of L2 norm and L1 norm. It has the curve on the bottom like L2, but it has linearity after the outside of the region. Right? This is basically the person who came up with this, picked that one and combined them. Right? It's called Huber loss. Now, the error basically is, so this is going to be sigma I minus sigma I. This is the error I. All right. So loss is going to be error I to the power of 2 if absolute value of error is less than whatever is that sigma. Okay. It's going to be sigma, basically positive, negative sigma. And sigma times error I plus sigma, not sigma I, sorry. Sigma. It's sigma to the power of if absolute value of error is greater than sigma. Let me see if it's to the power of 2 or 2 sigma. Totally the opposite is minus sigma minus sigma 2 over 2 sigma 2, yeah, okay. So so basically it tells you if you are within this range, that's the error value. If you're outside of this range, that's the error value. Okay. Now, if you take a derivation of this, derivation of Li with respect to this Li, what you will get here is that for the first one, or let's just plot this. That's the derivation of this function. Within this range, the derivation is going to be linear, is E. Outside of that range is going to be constant. Right? So the way that this this Huber loss works is that the logic behind it is that if you are within at some range, and here you see we have sigma. That means you decide what is the range. If the error is within the range sigma to minus plus to minus, I'm going to apply the gradient as a whatever is the value of the error. That's the gradient. As soon as you exit that area, doesn't matter how large is the error, it's going to be constant. For any large error, the gradient is always basically constant, right? And the the reason this basically works better than the other one is that because now you have a control over the sigma. So you're solving a problem. Now I take a look and I say that, okay, what's the range of the acceptable range of the error for me? It's between -100 to 100, for example. Then I set sigma to be 100, 100 to -100. And anything outside of that, I will basically have a constant gradient. So you first look at your data, get some idea of what's the acceptable error range that you're basically okay with. And then you set this sigma or sigma based on that, right? So that's called Hooper loss. Now, again, there are way too many cost functions or loss function out there. It's our goal is not to learn all of them. It's just to get some idea of when you want to choose your cost function, try to think ahead of time. Okay, which cost function makes sense? Read about those cost function. What is the pros and what's the cons of those? Right? Based on that, make a decision what cost function to do. Because you might see a cost function that works really good for your data because based on, you think it works really good, but that cost function has some limitations after you apply, and you might spend lots of time. To be honest, I did that for like 2 weeks. I thought one cost function that I'm using is perfect, ended up being wrong, and I just wasted 2 weeks of development time. We had a good result, but as soon as I changed the cost function to something else, I got like 15% improvement. And again, it's really important. What you optimize for, it's really important. Yes?
Is it like a sigmoid?
Sigmoid.
Is it better?
Can you explain this again?
Yeah, let me answer that. So sigmoid. So sigmoid is not a cost function. Sigmoid is a function that whatever value you give to it, it converges, it squeezes it to range 0 and 1. So sigmoid, just for the rest of you, sigmoid is a function looks like this. Right, this is 0.5, and the maximum is 1. Whatever z you pass to sigmoid, it would squeeze it to range 0 and 1. So it's not a cost function, it's actually output. When you want to do binary classification, which we will talk about it, that means you need to predict a probability. Is it dog or cat? The model doesn't tell you is it dog or cat. Model gives you a probability. What is the chance of being dog? What's the chance of being cat? So in order to get that probability, you need to squeeze whatever is the output of your model to range 0 and 1. So that's where you use sigma. We will talk about that in classification. What was that?
It's a squeeze or a benchmark?
It's squeeze or?
It's a squeeze like to convert the value between 0.5 or 1, or it's a benchmark, like if it goes above 0.5, it will convert to this classification, or if it goes below 0.5, it will convert to other classification.
What that means, right?
I'm saying that it's a kind of a benchmark, a threshold. If it goes above.
No, okay. Let's just talk about this. This is not part of today's class, but just to clarify what he says. This 0.5 that you see, imagine I have a model that is supposed to tell me that buy or sell a stock market. And the model tells you that your goal is to buy, so when you want to do any binary classification, you need to choose what's more important for you, buy or sell, one of those two. Because if I know one, the other one becomes 1 minus that, right? So your model basically going to give you probability of buying. It tells you if you you ask the model, should I buy today? It says, I'm 80% sure buy. That means I'm 20% say to not to buy, right? It's your decision where you draw this line, the threshold. It's your decision to say 80% is good or bad. Maybe I want to buy if the model is 90% and above, sure. That's the threshold. But that's not a baseline, that's just a squeezing function. Okay, let's stay focused on what we have. Any question with respect to this one? All right. So these are different cost function, and again, you just need to see which one works better for your problem and use that. Now, we want to talk about something that you're going to deal with it a lot and called overfitting. Okay, so any of you, anywhere you work, doesn't matter the company, when you develop a model, this is going to be your number one problem, concept of overfitting, right? So in a lame term, overfitting means that if I develop a model in the lab, or basically in a local machine on a data that we have, and your model performs really good, like 99% F1 score, or accuracy, or error almost zero. But as soon as you try that model on the holdout set, or train set, or test set, or validation set that you have, you see a huge drop in the result. That's called overfitting, because your model overfitted to the training data, right? Now, let's assume I have this data set. I have this point, this point, this point, and this point. I have 4 points, okay. So this is x1 and this is y. So xi basically is 1 and x1 by default. And n is I have 4 data points. So first time you develop a model, y1, basically it's going to be theta 0 plus theta 1 x1, right? And that model basically is going to be, let's say, something like that. So y1. Then I'm like, okay, I know the model didn't learn. I'm going to do some expansion, basis expansion. I'm going to create new features. And I come up with a new features. It's going to be theta 1 x1 plus theta 2 x1. That's x1 is just an idea. So it could be anything. Okay, this could be anything. It doesn't necessarily need to be x1. So now I get a model basically looks like that. And again, also these lines that I'm drawing is just an idea. Okay, it's not a real line. Then I'm like, okay, let me see if I can make this better. So I would create another features. x1 2 plus theta 3 x1 3. Right. Now I have a line basically something like that. And I'm like, okay, what if I can make this better? So I create and now I have a line that goes through all the data points, right? So when you are looking at these models that we created, somewhere around here or here, it's a good model. We don't know which one, you need to analyze it, but somewhere around, why not here? How many data points you have? How many columns you have now? 4. No, 5, theta 0 also. So now you have more columns than data records. So you see, that's one of the quick problems that will lead to overfitting, because you don't have enough data to learn this. You're just forcing the model to give you the perfect answer, right? So just to give you an idea. So when you work on any project, if you don't develop new set of features, your model going to underfit is going to not learn the proper, basically, mapping. If you go to higher dimension, if you do it too much, you end up with overfitting. Because your model basically, you keep creating features in order for your model to give you a perfect answer, right? Your goal or your job as data scientist is that any time you develop a model, before passing this model to a different team and says that this is ready, let's deploy it or whatever, is to understand if my model is overfitting or underfitting. You need to always do that, doesn't matter, right? They always will ask, we will talk about it further, but they ask you that what's the performance of this model, right? So what does that mean? That means you need to check for overfitting, especially overfitting, because it's so easy to overfit, right? You can easily basically solve a simple model, simple problem, but your model basically overfitting. But why? Because if you think about it, a model is simply a mathematical equation, right? You are telling to this model, minimize this for me at any cost, minimize it. So it will overfit. It finds the perfect data that minimizes the error on your training data. But Yeah, that you asked me to minimize it, I minimize it to 0. But as soon as you apply it somewhere else, it doesn't work. Think about it here. If I pick this line as a model, imagine you have it as a model. It's like this is a line, and I give it to you, customer, and says, hey, put it on your data set, just the same line. It doesn't work. Right, so that's the problem that you're going to have. So now when we talk about overfitting, there are ways that you can understand the overfitting. One common practice is to look at the values of theta. Okay, the theta that your model will learn. Large theta normally, majority of time, means overfitting. So when you get large values of theta, that's normally is a sign of overfitting. So think about this. I'm trying to solve a problem, and I have like hundreds of columns. My model, because I created so many columns, right? My model understand that, okay, I don't need all of these columns. If I simply use this one column, I'm going to have the lowest error. So it gives a high theta, for example, to 1, 2, or some columns, and the rest of them almost 0. That's large values of theta means your model is memorizing the answer. It's not learning. It just picks some columns because this is going to give me the best answer. So large value of theta means overfitting. We know by default theta is a vector, right? D by 1. If I have D columns, I'm going to learn 1 theta per column, right? Theta 1 all the way to theta D. That's right. So now we want to talk about this. Okay, how could we basically monitor, or basically how could we basically avoid this overfitting concept? Now, it's not that it's always will happen, because I say large theta is a sign of overfitting. It's not guaranteed to be overfitting, right? It's a sign. So you need to, if you see that, you basically need to analyze your model to see that if it's overfitting or not. But how could we basically avoid it? So the technique that we're going to talk about is called regularization. Okay. As the name comes, this technique, regularization, you're going to regularize something. I guess like it's kind of defining some boundaries, some rules, right? So regularization says that I do know, listen to this carefully. So I do know large theta means overfitting, right? So my goal is to J of theta. If this was, let's call it actually any J of theta, let's say. My goal is to find an optimal value of theta as argmean of J of theta, whatever is the cost function. That's the goal that you have. Find the theta that minimizes that, right? We know that by model will pick a large set of thetas, and to give this value to almost 0, and that will overfit. So if I know large theta can lead to overfit, I'm going to regularize this term. How? I'm going to add something here called lambda times f of theta. I'm going to add a term to the cost function that I have. So this was the cost function. Now I add a term to it. This term we call as a penalty term. Penalty term. Okay. The lambda is called regularization parameter. And f of theta is a function that gets theta and produce a number, okay, a positive. It's not a real number. Produce a positive scalar. Okay, so lambda is a scalar. Scalar is also positive. Sorry, lambda, not. F of theta is any function that you pass theta to it and gives you one positive value. Theta is a vector. That means f is a function that gets a vector as an input, right? And gives you a number, like a norm. It should be positive. That means that's why norm works really good. But let's try to understand what's happening here. So we are trying to minimize the cost function, but we know the model by default, in order to minimize that, it will overfit. That means it will pick some thetas to be large and drops the rest, right? So if I know large theta means overfitting, I will pick that knowledge and add it to the cost function. What does that mean? F of theta. F is a function that gets the theta, right? Like a norm, for example. If your thetas are large, what do you get here? Something large, right? So you see, this becomes something large. But what was the goal? Our goal was to minimize this, right? So I had this goal that I want to minimize the error, but now I'm adding something to it. This is kind of contradicting, right? Because I was minimizing, why are you adding to it? So from the model perspective, you tell to the model, you minimize this, but there's a penalty. If you pick large theta, this is going to be a penalty because this becomes large, right? So what will happen is, let's say I have this say this is the error, right? So I pick my model, basically gives me an error for training data. This is the error that goes down, almost goes to zero. This is the error of the training data. Now, a sign of overfitting is, you remember when we did gradient descent, I had that list called errors, and I was keep adding the errors to it. So it's a good practice that anytime you develop a model, keep track of the errors and later visualize them. So this is the index or T. As at the beginning, your error is large. As you move forward, the error goes down. So sign of overfitting is that if I plot this, you see that training error goes really down. But same time, if I also visualize the validation error, so what will happen here is that at time t equals 0, your validation error is going to be less than training because you already have learned something. So validation error starts somewhere around here and goes, and goes up. If you see something like this in your errors, that's definitely overfitting. Because what's happening is that your validation is decreasing. At some point, it start increasing because your model is only minimizing the training error, right? So large theta is one sign. The other one is that just visualize your errors. If you see any movement upward, that means you're starting from that point forward, you're starting to overfit, right? So, okay, I know this is going to happen. And here, basically, I'm saying that I'm trying to minimize this, right? So the model for training error, it basically was minimizing. Basically, it was minimizing to go to 0. But now you added a penalty term to it. You tell to the model, if your theta is large, you need to add that to your error. So if the error was 0, which is essentially, I need multiple pages. Let's say we have j of theta plus lambda f of theta. So let's say your model gives this one 0, perfectly drops the training error to 0 by picking large thetas. When you have this term here, f of theta, which again doesn't matter which norm you will use, a norm over a vector of theta, which there are some large theta in it, this is going to be a large value, right? So it's going to be large. So you were supposed to pick the theta that gives you the minimum of this, right? But your error is large. What do you think in the next iteration your model will, for example, try to do? It's just a conceptual. What's that? If this iteration is 0 plus large, what do you think next time your model will try to do?
Try to increase the j theta.
Increase
the j theta to reduce the penalty.
Well, it's a correct concept, but you're saying it in the wrong direction. It doesn't increase the j theta. It focuses on making this one to 0. So it basically drops this almost to 0. This is just conceptual, right? It doesn't do that directly. But it tries to make that minimum. If this is minimum, it means let's say all your thetas are 0 because you want that number to be 0. What will happen to this? It goes up, right? So this becomes large. So basically, your model is that there are both ends. If I make first one 0, the other one is large. If you make the other one large, first one becomes the other one 0, the first one becomes large, right? So now your model figures out, okay, I need to play between these two. I need to find a balance. So I shouldn't have this to go to 0. So I need to pick a theta that keeps this one as minimum possible and this one at the same time minimum as possible. So when you plot that, that error function basically will look like something like this now. Right? And for validation, hopefully, basically you have something like this. It probably train is going to be a bit lower, yeah. Your validation is going to be a curve like that. Now that is a type of curve basically you hope for it. Sometimes validation could be even lower, like this. But what you want is a consistent trajectory between train and validation. You want it that means that your model performs the same over a data that it was trained on versus the data it was validated on. Right? So that will be a consistent trajectory. And that simply happens by putting a penalty on the parameters of the model. Because the parameters are, again, are where all you learn are those parameters, right? If you learn this to overfit, this becomes large. So by basically using a technique like this, you avoid overfitting. It doesn't talk about underfitting technically. It's for overfitting because we are penalizing it for large values of theta, right? Think about the example of, imagine you are building a house, right? And you go to the city and you need to get some permits, right? And in the permits, it says that whatever you need to use should be these degrees. Like for example, for bricks, for pipes and everything, there's a degree. You cannot go like A, B, C, you cannot go below that, right? Whatever product you buy. And your goal is to minimize the cost of building the property. So you want to minimize that as possible. But you have a penalty. If you pick the cheapest product, I will penalize you. So the cost will later go up. That's the same concept here. You want to minimize, the model wants to minimize, but you put a penalty. If you pick a large theta, larger than something, you're going to get penalized. We're going to talk about this in details now, like what's a large theta or how do you penalize that, right? So now, is that clear so far? Right. So now let's start. So far we just say j of theta. Now let's define some function. So first one we're going to introduce. Actually, we're going to talk about something called regression. So far we have learned the simple linear regression. We have talked about the robust regression. And also we have talked about the linear regression if you use some basis expansion to basically go higher dimension. Right? The next one of the most important type of regressions for you is a ridge regression. Right? Ridge regression is that if I choose the following cost function, a norm 2 plus a norm 2 over my theta. So the penalty term, this function, is going to be a norm 2 over thetas. So if you want to memorize ridge regression, norm 2 and norm 2. That's a ridge regression. Norm 2 cost function, norm 2 penalty term. Right? Because again, theta is a vector, so you want a function that gets a vector, gives you a positive answer, positive value. So norm is the perfect one. If you pick norm 2 and norm 2, this becomes ridge regression. Now, let's use this. So we're going to first go over the closed form solution. then we go to gradient descent on this problem, and then so before we move forward, can anyone tell me that? Do you think this is convex or not? Why?
Because it's a norm, and norm should be convex.
Which one?
Both are norm too, so it should be convex.
So the definition becomes convex plus convex is always convex. Doesn't matter how many convex you have there. Just keep that in mind. If you use everything convex is together is convex. Okay, so it's convex. Another way of thinking about it is that you always add something positive to each other. So it's always going to be convex. Now, so for closed form solution, that means we need to take a derivation of this. So we can take that and set it to 0. So the first part we already done in the previous class, so I think that becomes 2 x transpose x theta minus, we had 2 x transpose y. That was the derivation of this one. And then we have this one. What's the derivation of this with respect to theta? 2. What happened to the lambda? 2 lambda theta. Right. So plus 2 lambda theta. Right? So closed form solution, that means you want to set it to 0, solve for it, right? So we set this to 0, get rid of all those 2's. Now we have a theta in both location here. So basically we end up with theta times x theta x plus lambda minus x transpose y equals to 0. X transpose x is a matrix d by d, right? Because x is n by d, x transpose x becomes d by d. D by d plus lambda, which is a scalar, is not possible. What should you do? You cannot do a matrix plus 5. What would you do? Multiply by identity matrix. So that's the only reason we do that, because lambda is a scalar. You cannot add it to a matrix, right? So now theta star becomes x transpose y over x transpose x plus lambda I. That means x transpose x plus lambda I inverse x transpose y, right? So this term, see if it's your in-class problem or not. Is that invertible? Yeah, that's your in-class problem, actually.
Yes.
Why?
Square matrix.
A square matrix is not necessarily always full rank. We proved in the previous class. There was a scenario it could be not full rank, right? If number of columns was more than number of rows.
So yeah, d is greater than.
So I leave this one to you to think. In order to prove it, try to use the concept. We had this linear dependency. If you have set of vectors, you could prove they are linear dependent. And rank of the matrix was maximum number of linearly independent rows or columns. You can use that to prove this is invertible. And this is always invertible, actually. This is always invertible. This term. I will leave that to prove. Okay. So that's when you be your theta star. But what is the difference here? So previously, when we solved for linear regression, we do the regularization, we got this. Right? Now what did we get? Plus lambda I. So simply, in order to regularize the regression, all we need to do is to add lambda to this matrix. That becomes regularized the regularized linear regression and closed form solution. Now, if we go for gradient descent, we know theta at time t equal previous theta minus this divided by gradient of theta, gradient of cost function with respect to theta at the previous time step. So we took a derivation. This was the gradient. This was the gradient before we set it equal to 0. In gradient descent, that means you couldn't basically solve it in a closed form solution, right? You might say that, oh, if this is always invertible, then we always can solve it using closed form solution. No, remember the cost problem, invert of a large matrix, you cannot. So you might end up going to do gradient descent because the data set is large and you cannot do closed form solution. So this gradient term is basically, we have 2x transpose x theta minus 2x transpose y plus 2 lambda theta. So we cannot set it to 0. We're just going to simplify it. So x transpose, let's say 2x transpose x theta minus y plus 2 lambda theta. I actually get rid of the 2's because it's just. It also technically, when you want to prove this, remember those 2 comes because we took norms to the power of 2. So you need to definitely put 1/2 behind it so they cancel each other always. So just keep that in mind. So I have x theta, x transpose times x theta minus y plus lambda times theta. So if you put that here, your theta at time t becomes theta at time t minus 1 minus learning rate times x transpose times x theta at time t minus 1 minus y plus lambda theta t minus 1. Okay. So that's going to be the gradient descent. That's it. That's the gradient term. I just replaced it here. Now, if you're looking at this term, which is, again, this is the same thing. The only difference here is that I use theta t minus 1 at previous time step. If you look at this term, what is this? X theta minus y. It is predicted. X theta is predicted. X theta minus y is error. So basically, in order to calculate the gradient, what we are doing, we're multiplying the data by the error. That's the definition of gradient. In a regularized version, we add lambda times theta to it. This lambda times theta acts like a memory. It's kind of like a memory. So we know what's the gradient, but we also say that whatever is the gradient, I know from before that theta t minus 1 is this value, multiplied by some scalar and add it to the gradient. So that acts as a memory. It's just kind of like ahead of time that if you want to update, if the gradient says to, for example, to deduct 5, I already have a knowledge that theta was this. Add this to that 5, maybe either becomes smaller or larger. It's kind of helping with the regularizing the thetas, right? Now, does this make sense? Everyone is clear? Which is basically, this is again error times theta times x plus a memory. And you don't need to memorize it this way. It's just a derivation of the cost function with respect to theta. Okay. But if you want to intuitively understand it, whatever is the error times the data gives you the gradient. But if you have some prior knowledge on the values of theta, because you don't want a large theta, so you add that to your gradient. That way you force it to have a smaller value of theta. So I should do it. So we haven't talked about lambdas yet. We just said lambda. So let's talk about lambda before we move forward. So lambda is a regularization parameter, right? That means it's a hyperparameter. What was the definition of hyperparameter? Exactly. We pick before modeling, you set the hyperparameter to some number, right? Like similar to learning rate, right? So lambda is a hyperparameter. It's fixed. That means you cannot decay the values of lambda. Keep that in mind. Why you cannot decay it? Anyone can make it guess that why I couldn't pick large lambda and then decay as time goes.
Just over because they were trying to continue to match like the multiplication, so like the error was still reduced.
So let's say I think you're in the correct scenario, but let me break it down first. So let's say lambda, we are going to pick lambda, right? So if I pick lambda to be a small, it cannot be negative. So a small means something less than 1, like 0.00 something, right? Example, lambda equal 1 e to the power of -5, right? Let's see what's the impact of that. So you are trying to minimize this j of theta plus lambda f of theta, correct? You will find the theta that minimizes. So if this is a small, super small, what do you think will happen?
Theta will be large.
What was that?
The j theta will be large. The cost will be large.
Not j of theta.
Model won't like realize like there is anything additionally you are trying to add.
That's correct. This, if this is a small, doesn't matter how large is this multiplication is always, so model will overfit. Picks a large theta because doesn't matter how large are my theta, this multiplication is always small. So this gives you overfitting. Now, what if lambda is large? Like for example, lambda equal 10.
Minimizing will become expensive.
No, someone said.
J theta is large.
So if lambda is large, what will happen to this term?
It will
Large, the main errors will never be focused on.
So what do you think model will do?
Try to minimize this function rather than.
This one.
Yeah.
So model forces this to go to 0 because this is large. And because this is also 0, this also goes up because thetas, if your thetas are 0, your model didn't learn anything. So the error is also large, right? So this becomes underfitting. Right? Because this becomes large plus 0. Right? So think about it this way that when you think about the concept of underfitting, overfitting, if this one is large, right? That doesn't mean your model didn't overfit. Okay, there is no guarantee. If this is large, let's say this is not large, but this is large, that doesn't mean your model overfit, but it means your model underfit. So it's because you might have a model that has a large error on your training data, but when you apply to a validation data, the error is consistent. It is large still, same ratio. So that doesn't mean overfitting, it means underfitting, right? But the other way around doesn't go. That means that if this one is 0 and this one is large because of this one is 0. No, if this one is large, so this is large because the thetas were large and the error was small, that doesn't mean definitely you didn't underfit either. Because it could happen. You need to visualize it. Look at the errors that you have: validation error, train error, and make some educated guess that am I underfitting, am I overfitting? Majority of time, large theta will tell you overfitting, right? But again, for underfitting, you need to be a bit more careful. You cannot just call it underfitting. It might be actually the model performs fine, But what you want to write and focus on is lambda. So be careful on the values of lambda that you select. You need to try different lambdas to find out which one is the best, right? So we will talk about that next. Let's take 5 minutes break or 10 minutes break, and then we continue. Who has the names? Is there anyone here? They didn't write their name. So write it now. Right. And I hope you didn't add any of your friends' name because I put names on it now. I'm going to go through the same practice again. Yes.
I do feel like. I'm so sorry about this, but I actually got engaged.
Use this model, this is our for this published papers, is that this is the baseline. Or you pick your features and do a logistic regression, that's your baseline. Based on this concept, don't tweak the baseline. That's lambda, that's not.
That's not right.
That's the regularization problem. These are two different algorithms.
Yeah, I just got confused.
No, that's gradient descent learning rate. This is a regularization.
Regularization.
Yeah.
So what's the shape of this? Like if you pick the correct lambda.
It's con.
It's like a hyperparameter.
Lambda is just but this is at the end is a convex.
So how we basically pick the correct lambda?
Lambda and convergence, they are not related here. Like it impacts the solution that you get. It's not about the trajectory of it. So I get two different things.
Because I'm more confused with the.
They are two different.
They're two different things.
Yeah, but I know.
Let me take a look. And I need to just count to see how many groups we have based on what we call. Because if we're told with 6 and everyone wants to become 6, then there's all. It will decrease, but then also the amount of basically contribution that every person has in the project also will decrease. The learning also goes down. Something I didn't mind that I will forget that, but to me, yeah.
Lambda value and the J of theta value so that it doesn't overfit and
So how do you find the lambda?
no the median value over here.
So these two together are convex. Right? This one, where did we write it? Just had it somewhere around here. This one plus this one, in the example that linear regression we showed, this is a convex function. So there is, it still looks like that concept. So you want to go to the minimum, that's so, and everything is around the theta. Theta that gives you the minimum total error, summation of this plus that.
So it's all trial and error like.
Right. That's right. If it has a closed form solution, you can solve it with one shot. Otherwise, it's going to be gradients and iterating. ये सब याद रखना है
According to the
interpretation. The same book.
I'm just refreshing it again, the same way he was explaining it.
The bishop. Bishop is one of the sources I know, and even if you think in class,
But I did not able to understand the HTML part of that. Like it was the way of readiness. I did not understand. I'm expecting like some.
We'll have it get to that. Okay, who has the name? Where does it go?
That's why when you said your name.
Just a scale. Just a scale. No, it's so, okay. Where's here? Where does this go? Just cancel each other and take it. So, yeah, there's two things, that's why I said they cancel, because you took it to the power of two, you need to get rid of.
So if I don't even get rid of it, then here it will proceed to be with time slope, right?
So you need to get rid of it.
Okay.
Because this technically is a 1/2 behind. We can talk about it. Yes. I did that. Yeah, yeah. Okay, who has the part? You have So okay, before we continue, I'm going to write a question here. I'm gonna write a question and give 5 points whoever can answer it. Okay. Let's look at this, whatever we have in front of us. Your friend asked that why I did get rid of these twos. How could I do that? It's like why do you get rid of it? And my hint was that technically I took this to the power of 2 to get rid of the square root. But if you do that, you basically add a 1/2 behind. So later when you take a derivation, whatever is the power of 2, the 2 and cancel each other. I wanted someone here, again, I give you 5 minutes and 5 points to tell me why this lambda over 2 or lambda doesn't make sense. Like why I can't just simply drop the over 1/2 and I just say the lambda rather than lambda over 2. So I'm saying, so lambda should be lambda over 2, but I'm using lambda. Why that works? 5 minutes, think about it. Well, basically, what you want to think about is that why that 1/2 concept, that the scaling doesn't technically has any impact on the learning.
The lambda we select would be very small, like 0 points. So pi 2 is.
Lambda is not a fixed value, right? We can change the value of that. So
Lambda is a fixed value. It is a fixed value.
We can change the value of lambda, right? So if you consider pi 2, we can increase the value of lambda.
But you cannot change the value of lambda in training. You pick one and that's it. And next time you pick a different lambda and you continue.
Because lambda is a scalar and like dividing a scalar by 2 gives a scalar, something like that.
Ignore the lambda. Like, what about this one? It should be 1/2. Why I'm not taking it into account? That technically it should be 1/2 behind whatever is here.
Because we need to get we need to get an average of like both of them, not this one being that becomes that becomes 2 theta, so it anyway gets cancelled. It remains lambda.
The 1/2, you see this 1/2 should be here technically.
Yeah.
We cancel it if we take derivation.
Yeah.
But if you don't take derivation and you want to calculate the cost, it's always there.
Yeah.
Why it's not important? Why I can't just simply say it, ignore it? Like there's a 1/2 under everything, but I'm just ignoring it. Why do you think what that 1/2 will do to the learning? Does it do anything? If not, why?
The rate of change.
It remains the same.
The rate of change will remain the same when you are looking at the same.
The rate of change will remain the same. Let's him clarify first. The rate of change will remain the same and
Like when you are doing it by 2 in all the change of the loss difference between the every data point could be the same for every 2 different rows.
actually that's correct. So doesn't matter. I divide everything by 2, right? Everything is the same. I just whatever I do it, I divide it by 2. This divided by 2, this divided by 2. Right? The model should learn the same thing. Because you just, if the error is 100, you divide it by 2, see it's 50. Same for the other one, right? So that's why This 1/2, I don't need to write it because when we learn, it doesn't do anything actually. It's just basically scale the value. You're going to end up with the same result. But the benefit of that is if you take a derivation, now you can get rid of those 2's. It just remind me later for anyone here also, if I told in the class you get a point, you need to remind me because I forget. It's your point, not mine. So keep that in mind. All right. So next thing we want to go over is called. Yeah, he's happy. Lasso regression. Okay. So the other important, really important type of regression is lasso. So reach is one, lasso is the other one. And trust me, it's a really easy set of interview questions. Someone asked me that, can you describe reach and lasso and what's the difference between and which one you select and when, at what time? It's a type of question that I will ask in the interview, to be honest. Like, you want to quickly, nothing technical, you want to quickly see that if the person has read the book or not. You basically ask that. So lasso regression basically tells you that if I have this norm 2 cost function and I use the error function or the penalty term of norm 1, norm 2 plus norm 1, that becomes lasso regression. Okay, so norm 2 cost function, same thing, but the penalty term you're using norm 1. Okay, so now because if we are not going to take derivation of this because of norm 1, it's not that easy to take a derivation of this because it is absolute value. It's not differentiable at its minimal, so we don't need to go through that for this class. But all you need to do is that we know it's differentiable. It's still convex because any norm is convex. So you're supposed to prove it for E plus problem. The convex plus convex is convex, so you can reach to minimum. Now, for any general, because we say you can use any norm as that penalty term, that means that you could write this as a following form, and norm degree P. Because again, norm, remember, had a general formula of degree P. So you can have any norm basically here as your penalty term. Now, you want to, so far we are just talking about using different functions as a penalty term, but I don't think it makes much difference to you because you're like, okay, I use this one versus that one, right? Now let's understand how did they look in reality. If I pick P to be 0.5, norm 0.5, the penalty term, the function looks like this. There's a belly curve here, so that's P equal 0.5. If you pick P equal 1, norm 1, then that's going to be the shape of that penalty term. And this is a 2D version. Let's just clarify. The 2D scenario. That means this is theta 1, this is theta 2. Same theta 1. I cannot draw it more than 2D, so just keep that. If I go P equal 2, which is norm 2, what do you think is the shape? The circle, right? So theta 1, theta 2. And these are all, some of them are in your book. If you pick norm equal 4, P equal 4, it actually looks like this. It's kind of like a straight on top, and on the corners are like basically round. Now, we want to understand what is I want you to understand the shape and why it's important. So when we do regularization and we use this norms as penalty term, that has a meaning basically. It's not just we penalize the value of theta, right? Because these norms are a function over theta, correct? That means that for if I have theta equal theta 1 and theta 2, correct? That's your theta. And these values could be anything. If you learn it in an iterative way, first guess, let's say I will do it at time 0, I guess 0 and 0. Next time iteration, I update, I keep doing that, correct? So if I want to find the shape of norm 2 for these thetas, if I want to visualize it, what would you do? I would basically, I have theta 1 and I have theta 2, correct? Let's keep picking here. I'm not able to plot that, but you need need to have a J of theta. This is the third dimension. I cannot plot that technically how we have this. But basically all you need to do is that for any value of theta 1 and theta 2, sorry, f of theta, not J of theta, f of theta, that norm 2, which is a norm, gets a vector, right? You pass this one to the norm 2, you get a number. And you put that number here. And you keep for different combination of theta 1 and theta, you get all those numbers. If you plot that, connect them together, that's how it looks like. For different theta 1 and through theta 2, because theta 1 and theta 2, again, for 2 dimension, are either positive or negative, right? So theta 1 here is positive, here is negative. Theta 2 positive, theta 2 negative. And depending on from where you pick these thetas, you get a different f of theta for that. Does that make sense so far? Yeah. So now, in reality, if again, I'm just going to stay with 2D because it's going to be harder to draw 3D. If I develop a model without regularization, okay. And this point here, let's say this point in means J of theta is minimum, the minimum point. It's like I'm almost 0, right? That point. So that point has a corresponding theta 1, corresponding theta 2. And as again, this is just a scaling issue, but they are large. You see, they're much further out. That's the concept of overfitting. You get this theta 1 and theta to be large value, and the corresponding J of theta for that is going to be minimum. Okay, so that's how overfitting works. Now, when you regularize, you put a function over the thetas that you can select. That function, depending on which one you pick, creates a boundary. Okay, a boundary that goes through the origin. Let's say, for example, creates a boundary. That boundary is a penalty test. Basically, that tells you that if you pick theta 1 and theta 2 from this region, the penalty is low. If you pick theta 1 and theta 2 outside of this region, the penalty is high. So that concept of regularization, that penalty concept, you're regularizing the theta by enforcing it to be that it need to come from a given region, nothing outside of that. Think about it. Large theta means overfitting, right? So I make a decision and I say that theta cannot be more than this, more than that, more than this, more than that. I enforce it. I said theta should come from this region. Nothing large, nothing less. Okay? But that's the whole idea of regularization. You enforce a boundary for your theta that your model is only allowed to pick theta from that boundary. Now, we will learn this later, why this boundary looks like this, or why, for example, like a norm 2, there's a distribution behind it. We will break it down in the steps. But first, right now, what we want to learn is that regularization puts a defined boundary, says that you only are allowed to pick theta from here. Okay, so if I'm only allowed the theta from here, okay, I picked this 2 theta and I got the minimum. But now my error penalty term is large. So what happens here is that you guys know the contour plot, right? So your model from this point needs to basically start to going in a correct direction, basically goes down to reduce the value of theta 1 and theta 2, right? But how could we do that? So if this is the minimum point that I'm standing here, and at the first pass, I don't know what is the region that I want to go. If I'm standing here, I could turn around in 360 degree, any direction go, right? So that's the whole idea of this contour plot. Around the point, you can go 360 technically. And the size, this step size, let's say something like a standard deviation. What's the step size that you move? So, and then next time I go another step. But you see that it's basically the radius basically increases, and so on. Right? That's the whole idea of contour plot. You will see this contour plots a lot in machine learning or deep learning, and they're always around this cost. So there is a cost, minimum cost, and then you basically either you're going towards it, or in this scenario you're going away from, because you're overfitting. Now you need to go through a penalty. And think about the concept of the building the house, minimum cost. That's the limitations that you need to buy the product from this brands, for example, or this I don't know, like degree. So you keep going around. Basically, the model goes left, right, left, right, left, right, depending on what's the cost function that you are using, until it reaches to that region. That trajectory of moves exists. You know, it's either going to be lots of fluctuations. If you do gradient descent, it's going to be lots of fluctuation. If we do a stochastic gradient descent, it's going to be a bit faster. There are different optimization techniques, which we will see later, like ADAM, NADAM, RMS prop, that they're all focusing on how to move better toward the goal, rather than trying to up and down along. Gradient descent, because of that concept of moving, is actually going to jump a lot in the trajectory past the movement. But anyway, so you go. The moment that this contour plot touches that region, enters to that region, that's the point that you want to use. Because now I have the minimum error and I have the optimal, like an acceptable theta from the region. Now, you might enter from here, or you might enter, for example, from here, and you can see which one gives you a better, like this one has a different theta 1, theta 2 versus this one, right? So you basically take a look to see which one is better. But, so this is for ridge regression. So the whole idea of this regularization is that you enforce this boundary. Hey, your model, your learning theta, only pick the theta from this region. Now, the cost function doesn't need to be there. It could be, this could be from here. It doesn't need to be also exactly circular. It could be actually a language, right? Things like that. Any direction this could go, but it's going to be contours basically, right? Now, if we want to, I'd actually go from with the other one first. Let's draw the L1 norm also. So this is theta 2, theta 1. Because we say the L1 norm looks like that, right? So let's say again, this is the minimum. Touching at that point first. Now, so this is the same concept, right? Now we want to understand the difference between these two. Let's look at L2 norm. We minimize the values of theta until we entered this region, right? So both theta 1 and theta 2 are decreasing basically constantly. Like, you know, it's not with the same. Yesterday I used the wrong term. One of the students reminded me. It's not with the same ratio, but they are decreasing constantly together, right? So this both basically in the same speed, they are decreasing, right? So theta decrease its same, let's say, speed. Now, let's go here. If you are looking at this one, right? What will catch your eye? What could you say is special about this one versus the other? Just look at the plot that you see here. What's that? Touches on the x-axis here. What's about that? Theta 2 is 0. So because we entered from this corner, so theta 2 is here. What does that tell me? L1 regularization, okay? Lasso regularization, basically L1 regularization, does automatic feature selection. It does drop some of the parameters to 0 because the model is a feature selection technique. It tells you these features that the thetas are 0 are not useful. So if you want to do automatic feature selection, one of the most common one, actually really good one, is L1 norm. If you use L1 norm, doesn't matter how many features you have, it's fast, quick. Later, your model is trained. You basically, this is what you do. You have a data set. You bring a linear regression model, for example, or logistic regression, or what if it's classification. You use L1 norm, you train it one time, and then you go look at the thetas, see which one of them are 0. Then you drop those from your data set and you continue with whatever other model developments you want to do. So a future selection technique. So thetas might drop to 0, automatic feature selection. So that means if I'm developing a model I don't have a knowledge of, I don't want to spend time to do feature selection, I just simply use L1 norm and it does it for me. So keep that one in my automatic feature selection. But also it's not like that definitely something goes to 0. Maybe all features are important, right? So there's no guarantee that something goes to 0. Also here, you might have something that goes to 0. It's not like that an L2 norm doesn't give you 0. But it's really L1 norm will drop features. But why? Why do you think it's more common to enter from these points in L1 norm rather than entering from these points? If I create these contours on L2 norm, why do you think it's not that common to enter from those 0 points?
And L1 is extreme points are present.
Right. So try this later. To plot this on your, or maybe right now, plot it on your pen and paper, basically, and try to see if you keep drawing these contours, which location you will enter. The chance of entering at these edges here is really low at this axis points. Because of this curve, you always somehow touches some other points. But for this one, actually the odds are really low that you touch that first. You normally touch one of the corners first. Now it's possible that that happens, but it's really, it depends on the problem. That's why L1 norm, because of the shape of this boundary, it will normally drop some of the features for you. Now, if you want to, again, this is only for 2D. If you want to think about this as in a higher dimension, let's say if I have D dimensions and I plot this, so it doesn't look like a square anymore. If you have D dimension, this is kind of lots of sharp edges. It's like if you have a porcupine animal, and it just basically goes out, it's just all those basically sharp points that are coming out. Now, if you have a balloon and you drop the balloon, so many of those will enter. That's how it technically works. You have all these edges coming out. This cost function is, when it will touch on some of those points, and those are the ones that define which columns will need to be, you need to drop, because the theta for some of those columns goes to 0. So in higher dimensions, technically something like that happens. Because the students ask this question: is there a guarantee that it will basically touch? If you try to imagine that animal, it will guarantee you, it will basically, there are some sharp corners that it will happen. It's also possible not that, it's not something that doesn't happen because your data is really perfect. You already have done feature selection and it doesn't drop any features. But both of this technique, if you have multicollinearity, you need to use this. This one, because multicollinearity means that if I do feature expansion, basis expansion, I have so many features. They all already have correlation among them. So we already know that if you don't add features, you might have underfitting. If you add too many features, you might overfit. So, and when you do basis expansion, you end up with correlated features, right? So if you have a problem like that, these two both are helpful, basically. They will basically get rid of those features that they have a high correlations, especially L1 norm because it drops it, but L2 norm also, it will, it's possible because also this one, if you imagine in a higher dimension, it's possible that you enter from access point. So it will drop some of those some of those features to go to 0. Does that make sense? Everyone here, you understand L1 like a lasso and reach here. Yeah. All right. So again, and for different type of penalty term, the whole idea is the same. You just think where it will enter, right? Now, we will later talk about why these forms look like this. Again, there's a distribution behind this. That's why it looks like that. That's for the next class. All right. So, so far everything's simple, right? We need to tweak the materials a bit more. Every chapter, as we move forward, it's think about it that the materials that we learn are going to become harder and harder, right? This is just kind of like an entrance point here. So it's called Bias-Variance. And everyone here is ready for it. Trade-off. All right. Bias-Variance trade-off. Again, you as an engineer, when you develop a model, data scientist, you develop a model, you always test your model to see that if it's overfitting or is it underfitting, right? So, and that's, you basically do that using this bias-variance trade-off. So bias-variance trade-off helps you to come up with a number, which we call it expected loss. Okay, that's equal bias to the power of 2 plus variance plus noise. So there is a term called expected loss, and it comes from bias plus 2 to the power of 2 plus variance plus noise. Think about it from this perspective. You're working in a company, you develop a model, and then at the end, when you have a model, you pass that model to a team called product team, and basically they take care of whatever it is that to be sure that that product reaches to customer. One of the common questions that you will be asked is, okay, if we use this model, how much loss will we have? What's the expected error of your model, right? The question, someone might tell us that how accurate is your model? That's a good question. But the majority of time you will be asked how much error you will have. Because that's, if you are too good, people might say it's good, but as soon as you have error, everyone start talking, right? So it's kind of the other way around. Even if you have a small amount of error, they might talk about the error more than how good is the model, right? Especially, when you sell to a customer, unhappy customers, they always basically reach back to you. So you will be asked a question like this: that what's the expected loss, right? And that's where basically this term comes from, because you want to have some idea of that. The idea here is like this: expected loss. How much error I will have if I push my model to an environment that I haven't seen before, considering how much error I had on the environment that I trained on, plus some noise value. That's a bias variance trade-off. Error that comes from your own environment, how much your model will have error if you just use it on your own environment, how much error you will have in unseen environment, and how much random noise exists. That becomes the expected error, expected loss. Now, we know the bias term basically is it's an expected value of theta minus theta. That's the bias variance. This is just a statistical definition of it, right? Expected value of theta minus expected value of theta, right? Now, let's say this is the real source of all the data that for the task that you are working on. All the data can come from this region, like all possible data. It doesn't matter which country you are or whatever. Let's say this is all the data. Like if you do, for example, I don't know, I'm doing a classification on breed of animal, breed of dog, for example, that a user comes to upload a photo, I will tell what's the breed of dog, right? And these are all the possible images that I could have for all possible breeds from internet or wherever, right? So this is the sample space or domain space, basically, right? Now you have a data set which has x1, y1 all the way through x and y. You collect n data points. Each xi has d dimension, right? That's your data set. So if this is all the possible data in the world, the sample, the data set that you have for your model development is going to be a small portion of here, right? So it's going to be, for example, somewhere like here. That's the data set that you have. So that means data set comes from some distribution, probability of data set, right? Because this could be anywhere here. It comes from, is a random data set, right? You can think about it. If I think about the same example for breed of animals, you want to develop that. The easiest way for you to get labeled data is Google. Go on Google, search for dogs with breed, and then just millions of images will come, right? And let's say for your task, for your project, you want to download free data labeled already, and you start downloading. And let's say for 2 days, you have downloaded lots of data. A week later, if you go search again for breed of dogs, you're going to see new photos. Because you know the way that the Google search works is that the ranking changes, right? Now you have new set of photos that you haven't seen before. So you see the data is random. This is a random data set that comes from some actual distribution. So this is the whole data, that's the data that you have, and this comes from a distribution. So similar for X and Y also come from a distribution of X and Y, right? That means X is the features, Y is the target. So there should be a distribution, relationship between those two. Probability of X and Y happens together. Like probability of, I don't know, have be like, I don't know, 1 feet, brown, long tail, and being a dog is larger than probability of being a cat, right? So there is a probability between the feature and the label, correct? So that's so far the probability. So now we want to talk about a concept called expected label. So expected label. If I have for let's say for xi, okay, we might have basically yi comes from different, basically, let's write it differently. It comes from a distribution, or comes from a set of yi. What does that mean? For one example data point, let's look at the concept of price of the house. There is a complex, like for example, and this complex, when you go into complex, 1 bedroom, 2 bedroom, 3 bedroom, they're all exactly identical, right? It's like there's a really less variation among them. When you look, they are they're the same. The square feet is the same. Where's the window? Everything is the same, right? So and let's say different people, they go buy a unit in that complex. Year later, if someone wants to buy a 1-bedroom over there, do you think all those 1-bedrooms are exact same price? Price varies. Exact same, identical 1-bedroom, same floor. I want to sell mine higher, right? So that's what happens. For a given input, you actually in your data, you're going to see different labels, right? So example, that was an example of regression. Let's look at an example of a classification. Everyone, hopefully no one is sick, but everyone, for example, in this class, they go to a doctor, let's say, and the doctor basically look at the demographic, everything put together and says, for example, lots of similarities. And then let's say 1% or 2%, for example, is sick, has COVID. That's an easy one, right? And from a doctor perspective, you all are identical, like a characteristic, but only 2 has the disease, right? So you see the label, variation in the label, or for example, you want to make a classification, like you have downloaded this data, you find a dog and a cat, they're really a small one. Every characteristics that you have in your features, they are the same. You for example, a Chihuahua and a cat, you might say that, oh, this should, like, for some of the labels, you see dog, for some of the label, you see cat, right? Or you have hired some people to label your data for you, that's called human raters. Raters means someone you pay to label the data for. You either hire someone with domain expert or hire someone with free times, it's depending on what's the problem. But the domain expert so we have let's say in example again, healthcare, the easy one. I work in healthcare, that's why I always have examples. But let's say you want to you have MRI images and you want to label those. So you go hire 10 radiologists and says that, okay, I pay you this much, for example, that I have 100 images, and you give each 100 to every doctor. Go over it and tell me if you think this person has this, for example, cancer or disease or not. And you collect the answers. You don't find agreement on everything. You get different answers. Maybe 6 doctors say that someone has disease, 4 say they don't have disease. You see different labels, and that's common in practice. That is a common thing to happen. You either make a call, like for example, you say that majority votes, maybe. Let's say you say that if 6 says yes, you accept it. Or you actually need to go back to the result and try to understand why they are disagreeing with each other. That's reality. And that is your job as, to be honest, data science, machine learning engineer is your job. Otherwise, a company gives you a data, and from a company perspective, you have the data, you need to be able to do your job. So you need to actually go look at the labels and see that, does it make sense? Can I use this? You know, if you see inconsistency in your labels, look at those. And that's easy for you to do. If it's classification, do a group by and try to understand plot the distributions of the columns. If you see really variation, that okay, something is wrong. If it's regression, do average on the Y columns and see that what's the standard deviation of those Y values. If it's a really large range, something is wrong, right? So there are ways for you to monitor that. But for here, we say that X could get any value of Y, right? So if, again, let's go back to the house price. If someone comes to you and says that, hey, I want to buy a 1-bedroom house in this neighborhood, based on your data, what is the expected cost that I have? You see, that's a question, right? What's the expected cost? You basically put the average of 1 bedroom and says that it's going to on average be around this, right? Think about the linear regression. Where does the line goes through?
The average.
The average. All of those, because there are consistency, even for linear regression like this, if these points, they're one that close to each other, they're almost the same, similar. The price varies, so the line goes through the average of those expected label. Does that make sense so far? So now here, we want to calculate this expected value. if it's majority of time, let's say we're dealing with, if we're dealing with continuous, so it's going to be expected value of y, okay, given y given x. You are trying to find what's the expected value of a given y based on the x value, right? So if it's continuous, that's going to be a basic integration of y p of y given x p of x. If it's discrete, become summation of y p of y given x, right? So the expected value we had in the first class, I hope you remember that. So that's the expected label, which basically this is the same as average of all labels. That's what it does. Because any expected value is an average technically, right? So now two, our goal is to develop a algorithm or model or hypothesis, whatever, A. Okay, let's call it H. Algorithm H, hypothesis concept, right? This is your goal to learn that, right? That's the end goal that we have. And let's assume we have H theta xi. Let's assume you have solved it. You have that hypothesis, the algorithm. That means I have developed a model. The model is ready. So now I need to answer a question. What is the expected loss for that model? Okay, now I want to find what is the expected loss, right, for this model. Right? We assume we have this model. So we want to basically calculate the expected loss. Loss means H theta xi minus yi to the power of 2, because we want it to be positive, either absolute value or to the power of 2. Considering x and y are coming from this distribution. And also remember, this x and y are your validation data. It's not the training data. Expected loss, you're not basically calculating that one over the over your trained data. So I'm trying to see that if I have this sample data aside for this algorithm, how much error I'm going to have, expected error. But why this is expected error? Why not directly I calculate all the errors, right? Why it should be expected? Because you need to go back to this. Your data, training data is here, right? Let's say you have a validation data. This is my validation data. That is also a random data, could be anywhere here, right? So when you say expected error, it means that how much error I expect to see if I sample across this for this validation data. That's why we say expected error, not the exact deterministic error, right? So we assume x and y comes from some distribution, which this is which distribution, and we sample from, and we are going to calculate the average error for all those points. That's basically expected error, right? So that becomes x, y, h, theta, xi minus yi to the power of 2, because it's a probability of x and y, d of y, d of x. That's the expected value for error. And if it's discrete, here it's not going to be discrete, but if it was discrete, it becomes summation over that, right? So, okay, now I have the expected loss. Now let's add 3. So our data set is a random variable. Do you agree with that? Yeah. The data set that we have is a random variable because it's random from that domain. So any model developed over D is also a random variable. What does that mean? Every time you sample from this data, you go on Google, download a new data set, you develop a model, you're going to get a different model. If data is random, the model over that is going to be also random. Does that make sense? Yeah. So that means every one of you goes download for the same project, different data values, data sets from the same source, you're going to have a different models. So because we know data, the model, the algorithm that we are also learning is random, we are going to introduce something called expected model, or expected classifier, or expected algorithm. Right? Which in a lame term means that each one of you developed a model, average all of those models together. Or do an ensemble over all those models. That's the idea behind it, right? Because you have sampled different data sets, develop different models. Now you want to do a majority vote across them, for example. Or average the output all of them. Like you're making a price of the house. One model says 100K, the other one says 105, the other one says 110. Average all of that into one number. Expected values, right? So expected classifier basically says that if we show it with H bar, X, expected is given, it's an H, it's a D, because we developed it over the data set. Given the data set comes from some distribution, which we at the beginning, we say data set comes from a distribution, right? So that's also the same thing, basically, integration over D, H theta, the probability of D, which basically means that, you know, I have, for different data set, I develop a different model and I average those together. So, before I move forward, does this make sense so far? Anyone wants me to go over it again? No? All right. Go again. Which one? 1, 2, 3. Third one. So we are saying that the data set that I have could come from anywhere here. Could be this, could be this, could be this, right? It might even have overlap next time, right? Data set is random. Every time you go download this data set from Google, for example, or whatever, is a random data. Or every time, imagine you work in a company and you collect data from customers. Data source is the same, but you don't necessarily see the same customer every day. Like for 1 month, you might see a totally new set of customers, new data, right? So data set is going to be a random variable. Any model developed over a random data is going to be a random model. Again, every one of you is going to get a different model. What you want to do is that we basically say the expected model. If I have access to all possible data, right? What is the expected model? What's that classifier or the algorithm that I could have if I had access to all of this? Right? How could we calculate that? We basically do an average over all possible data that we collected and develop the model over and basically aggregate or average those models. But that's theory. In reality, you cannot do all of that, right? We will talk about that. But mathematically, that's the idea. Reality, that means, you know, maybe I have only 3 models. I do average over 3, or I have 5 models, or I do, for example, majority models. I don't need to go through all. But that basically, what he also tells you is that the one model, when you develop one model, is not good. If you want to understand that what is a good model could be, you need to develop multiple models over different data set samples, and have an aggregate or average across all of those. That becomes an expected behavior of the model. Okay. Now, if we 4. Okay, so now we define expected model, right? Now that means that different, like we have an average set of model, basically. Now we're going to calculate the expected error again. What? Okay, so this time, in order to calculate the expected error, we basically say, what's the expected h theta xi minus yi over of 2 for x and y that come from a distribution. This is the validation data example, and data set comes from is a random data set comes from a distribution. So we are combining all three now together. So this basically becomes, let's say, 12i, let's minus. This becomes the expected error now. We keep into account basically a couple of things. One is that x and y validation data comes from the distribution. Data could be random, so the model developed of it also will be random. So now if I want to answer the question of, if I use your model, what's the expected error I will see? You need to keep into account how your model will work over your validation data, how your model will work in compared to perfect model, like an average of models. That is this expected error, which or bias variance decomposition. How my model will work if I just pick this model, the one model that I have, and I run it over unseen data validation, and how my model works in compared to a perfect scenario model. That becomes that expected error. Now you have this in-class problem to basically break this down into that becomes expected value of so your goal is to break that integration into these three parts. We already have defined them here. You just need to basically expand that. Need to fix this one. This also will get an X. Y bar X. Y bar X. Okay. Now, what you see here, this one is called variance. This one is called bias over 2, and this one is noise. All right. What I want to do is that I'll pause on this three definition for a couple of minutes and see again 5 points. Anyone who could, in a lame language, break each one of these. You can do one also, you get points. But first thing, don't jump to answer. You want to give time to your friends. One at a time. Your goal is going to be describe what do you see in this variance, how in a lame language. And then what do you see in noise, what do you see in bias? We'll wait 3 minutes, not 5 minutes. Okay, just wait 3 minutes, then we'll give you time. Right, we'll start with variance. Who wants to go? All right.
So basically, you're trying to compare how your model is with a perfect model, the error between that,
So
basically.
what does that tell you?
The expected error between the.
Yeah, well, I see that. Well, what does it tell you?
So it tells you like how far you are from the ideal case with your model.
So that's correct. So variance tells you that if I have one model, developed one model, how far is that model with respect to an ideal model that I want to have, expected model? And that is the variance. When we see a model, remember for overfitting, we say high variance model. Why we say high variance? Because that means the error between your model and ideal model is large. And what does that mean? That means you develop this model as soon as you want to test it on an unseen set of data, validation data, the error is going to be large. But we are assuming that the error of average model over that unseen data should be small, right? That's the idea behind it. Now, how do you calculate the variance in a simple term? Is after you develop your model, you test it out on your validation data, calculate what's the average error, for example, over the validation data, and save it as a variance. So, developed model, test it out on unseen data, and you have an average error, that becomes the variance. Make sense? All right. So, noise, you wanted to go.
So that is why we are calculating the error for the before model and the error after adding the new data points. We find the square.
So this one, this is not the model. This is y bar x.
Predicted minus actually.
No.
Validated.
So the expected value.
The expected value of the.
Expected value is not a predicted. Y bar was number one.
Check the label.
Expected label.
Yeah, the label needs to be according to the data phase.
Anyone wants to go?
Like.
We already got. Is it?
For the noise one?
Yeah.
Yeah, so basically like the expected, like if there are a lot of expected labels for a certain input of X. So what we are doing is like we are just taking the consideration of another expected value over the whole data space that we have had.
Mhm.
And we are just calling it noise and adding it to the expected error so that we can get addition of like what will be the expected error after model is trained from varying.
You were going correct, then you diverged.
Like I thought like I should add some more
So
details.
first, there is nothing about model here. There's no model here in noise. Noise is basically tells you that I have this label Y, this in my data set. It's like my data set is for the house prediction. So for every house, I have a price. Then I go online and I search on Google, what's the average, what's the price of, expected price of one bedroom in each zip codes? Right? Google gives me average across all the possible data, right? For example, I compare that expected price with the price that I have in my data set. The gap between is noise. It's something that you cannot do anything about it. The label is expected to be these values, but you have something a bit off, different, right? So that's basically that's become the noise. Who wants to go bias? So I point out, want to go for bias?
Right.
Go ahead.
So the label that the expected model gives, and the expected label, so the difference between that.
What does that tell you? Okay, that you're on a correct path, but what it tells you?
How close it is to your ideals or the expected level.
How much is always expected?
Expected label.
It's not all the same, it's written over there, the gap between, but what does it tell you?
Like the consistent gap across an ideal model and ideal expected level.
That's the same thing, gap. So what does it tell you? Bias tells you that doesn't matter how many times you download data set and you average all the labels and you develop so many models over this, you're going to always have a gap between these two, which indicates this algorithm that you are using is not strong enough for solving this problem. Doesn't matter how many times you sample data. There is always an error for the best model and average basically label. That either means the algorithm is not strong enough, or means that it's not easy to learn. Your model is simple. It's simple scenario. So that's why when we say a model is high bias, means it's underfitting. That means you're not learning. Doesn't matter how many times you sample, how many times you average, you will still have error. Right? So that's the bias concept. We calculate the bias over the training data. So validation data, training data. What does that mean? After you develop the model for your project, which you need to have bias variance trade-off, on the training data, after you're done, over the same data, test the model, average the error. Error over the same data that was used for training. So your model is not going to be zero. You're still going to have training error. So that average training error is going to be your bias. Average training go to the power of 2, basically bias, right? Plus, for the variance, you use your validation data. And you see that if I use the model that I trained over a data set that I haven't seen, how much error I get. Plus, you look at the labels inconsistency, you find some noises. You sum those three together, becomes expected loss. Which again, what does it tell you? It tells you if I have a model, there is some error that model has over the same data set or environment. That means it doesn't matter if you use this data for training, your model still has error on this. That's the bias. If it's zero, that means your model is perfect, learned perfect from the bias perspective, but most likely variance goes up. Either of these two is there. You cannot set 1 to 0 without setting the other one hierarchy, right? So that's why you need to find a balance between. You want a model to have reasonable bias, reasonable variance. Then this way the summation is something reasonable, because it's like a concept of it, it's not the same, but do you remember the regularization one goes up, the other one goes down? Here is also the same thing. If you force bias to 0, that means you're overfitting. Variance goes high. That means if you pick that model, apply to unseen data, it doesn't work. Do you think this is clear? So this is called bias variance trade-off. It's actually one of the most important concepts for you, because again, doesn't matter what model you develop, doesn't matter which company you are at, you need to have its number before reporting the model. What is the expect? Like that means you have checked the model for overfitting, you have checked the model for underfitting. So that gives a sense to, hey, if we ship this to customer, we're going to have around this much error because we saw this much error over the same data, we saw this much error over the unseen data. Together, we're going to see around this much, and it's kind of like an average. These are average errors. Okay. Good. All right. So. All right, that is the unbiased variance trade-off. Now, let's talk about that lambda. In regularization, we had that lambda which we just talked about it, but we didn't say how we're going to select that. Because lambda is a hyperparameter that you cannot decay. Actually, we want to go to that. So let's say this is my lambda initial, and as time goes, my lambda goes down. Okay. Can anyone tell me that you cannot? Why I say you cannot do that? Lambda should be fixed. You cannot decay. That one also can get 2 points. You just tell me that why we cannot do that. This you cannot do that. Lambda should be fixed. You cannot decay.
J theta will like exponentially increase.
J of theta exponentially.
Like if you look on the reverse of this curve, you get a increasing curve for J theta. Because as lambda keeps coming down, the value of J theta keeps increasing because it chooses a higher theta values. So you automatically get a curve which is undesirable.
That's correct. So if lambda at the beginning is high, what will happen here? Lambda is high, theta goes to 0, right? And you see the model is perfect, working fine. As the time goes, lambda goes down, you reach to the point, you have a lambda which is good, it's balanced. But in the next iteration, if you change the lambda, all your learning is gone because the model quickly changed the thetas. The more you go down on the lambda, the thetas become larger. So you remember small lambda versus large lambda, overfitting, underfitting? That's why you cannot change it. If you change it, at the beginning you are, for example, underfitting. As you go forward, you're overfitting. So lambda should be fixed, one number at the beginning of the basically training. Now we want to talk about that, how we select that number. Also, actually, for the regularization, we already saw that x theta minus y, basically norm 2 plus norm 2 plus norm 1 reach lasso. But also, if you can pick x theta minus y norm 1 plus either of those two again. Or you could pick this as a Huber loss plus lambda norm 2 norm 1, right? So that concept is applicable to robust regression also. It's not just for norm 2 and norm 1. Any cost function that you have basically is a convex cost function. You can apply and basically norm 2 to it, or a norm to it basically.
Can we also take like a norm P, let's say like a random norm as well for lambda?
Yeah. All norms are basically convex.
Okay.
So, because the reason we say convex because it's important to be able to reach to a minima. So if you pick a function over theta which is non-convex, then the one main reason for convex was that it's always positive. So if you pick a function that produces a negative plus a negative, you see, it cannot be negative. It should be always positive as a penalty term. Also remember, we will talk about this. This is for minimization. What do you think if I was maximizing? Let's say my goal is to maximize J of theta.
You subtract the
You subtract the
Then you will add minus f of theta. Because you always want it to be the opposite. It's a penalty. We should be opposite, right? Okay. So we're going to talk about something called holdout set. Okay. So I have this sample data, right, or the data that I have, and let's call it D. That's D. And what you will do is that at the beginning of the project, shuffle the data first. Always shuffle the data. Don't just do random video shuffling. So shuffle the data, and then I have this called training data, and this is called holdout data. Okay. So we are interested to find a perfect value for lambda using this technique, for example. So what we do here is that I will initiate some lambdas from lambda 1 all the way to lambda p. So random lambda, maybe from 10 all the way to 0.001. Depending on how much time you have, you can put more. It's not practical to do that. The reality, you want to do something either like a binary search, grid search, random search, but this is a general form of how to basically select the lambda. So at the beginning, you initialize some random lambda, and you want to go over each lambda, develop a model, and then compare them and pick the best lambda. That's the idea. So you define errors, errors is simply an array. Then you write a loop for lambda I in those lambdas. You just can loop one item at a time. You're going to calculate the theta star as arg mean j of theta plus lambda f of theta over the train. So it doesn't matter what's the algorithm, what's the cost function. You pick that training data set and you find the optimal theta for that, correct? Then you calculate the error I, which becomes basically j of, or you can just write this summation or average, whatever, let's say average. 1 over length of the holdout. How many data points you have in the holdout? I belongs to the holdout, and you basically go over loss of xi. That means then I go over any data points I have here, calculate the error for that data point using this data that I just learned. Okay, so over the holdout using all this theta star lambda I. This is for lambda I, using theta star lambda. So I calculate the average error for the holdout set using the theta that I just learned here. Okay, so what's that?
Append the error back.
Oh yeah, append the error, right? Yeah. Just need to find more space. So next, basically, we do errors dot append error I, and that's it. So then end for loop. So what are we doing here? For different lambdas, we pick the training data, develop a model, test that model over a holdout set, store the error, and finish the loop. After this loop is done, what would you do? What would be your next step?
The max of the min of errors.
Pick the mean.
Yeah.
Right. So we will basically say lambda star is a lambda that gives you arg mean over the errors.
Yeah.
That becomes the optimal lambda. So you see, this is like a simple, basically brute search. It's just you have set of lambda, go through all of them and pick the one that is minimal. Now, at this point, when I'm done, when I have this optimal lambda, there are two ways that you can move forward with, depending on the problem that you are solving. But one way, for example, again, depending on whom you ask, also might answer be different, is I pick this lambda star and I go pick all data that I have, including the holdout set, and develop a new model because I have already my lambda now, right? So develop find theta for lambda star. The other one is that if for this lambda, I already solved it, I already know what's the theta, so I can use the same theta. Because you already solved this, found this theta, use theta star with the lambdas. So depending on whom you ask the question, the answer might be different. Either one should work, you know. But again, that's your call. Now, what do you think could be the problem with a technique like this, beside the loop-through concept? From the data perspective, what do you think could be?
Randomization basically can overlap.
No. That doesn't mean that's not the correct answer, but not a data problem. Now, ignore the for loop.
We consider a small portion of fold out data, let's say like 10% of fold out.
Okay.
So we might not capture the perfect, the shade of whatever.
That's correct. So, because I'm keeping a portion of my data out, there is no guarantee that the lambda that I'm learning is good, because there might be that portion that you picked might actually have so much predictive information, right? So this technique, holdout set, is not a wrong technique, but it's wrong if your data set is small. If you have a small amount of data, you cannot keep a portion of it out, because you don't have data. If you have a large data set, million, billions, then yeah, you can do that. Doesn't matter how much you send out, right? Because you have enough data. So you need to think, if your data set is large, that's fine. Because if data set is large, we divide the data set in reality in 3 parts: training, dev or validation, and test. And these are random and shuffle. You pick this training to develop your model. You pick this validation to guide your model, or to select the optimal answer, or to give the expected error, but this one, depending on which company you work, you either see it or you don't see it, right? It's common for some companies that the person who's working on the model actually don't have access to that data. Anyone make a guess why?
So you don't overfit.
How do you overfit?
Like you learn too much about the data.
So this is common, and which probably, if you think about it, you will do at the beginning at least. You develop the model, your model works good here, then you are like, before passing the model, let me see how does it work here. And you take a pick and you see, oh, the error here is large. So you go tweak your model, so the model gives a good error here, because you're going to use this for reporting, right? So it's common companies, you don't see that. Someone else has that data, they give me the model, and then they test your model, right? So it's that's also happens. If you have enough data, you divide it in the following format, and you use the data in different stages: training, validation, and that last one is just for final report. Okay, we use this data here. This is the error, basically. We are not tweaking anything. That's after you make a decision. Okay, this is the model we go, is not tweak it. Let's use this one. Now, we will talk about in next class what if we have a smaller data set, and we're going to learn a technique called k-fold cross-validation. So I know you have heard of it in data mining. We have worked with data mining. But we're going to understand why it works now. All right. See, the numbers were accurate this time.